Hi, this is Dr. G Vikas. In this session, we'll discuss about shear center topic. What is a shear center? Shear center is a point in the cross section of the structural member, such as beam or column, where the transverse shear force can be applied without causing any twisting or rotation of the member. So we know that for symmetrical bending, only bending occurs. Okay, suppose this is a cantilever beam fixed at one end, free at other end. Okay. Now, we know that what is symmetrical bending when plane of loading is coinciding with the plane of symmetry. Okay, then it is known as then it will bend about xx. That means xx will be shifted to some other some deflection will be there in this direction. Xx will be shifted downwards. Yy will be remain as it is. Okay, this is symmetrical bending. Only bending occurs about xx, no twisting here. But whereas whenever the plane of loading is not coinciding with the plane of symmetry, okay, then both bending and twisting occurs. That means it will bend about xx as well as yy. Xx will be changed, will go down, yy will go to the left side in this case. Okay, that means here twisting is also there, bending is also there. Okay, now what is shear center means? It is a point on a member where the shear force can be applied without any twisting. Okay, if we apply any shear force, there will be no twisting or no rotation, only bending will be there. So when the load is applied at the shear center, the beam will bend but not twist. Okay, when the load is applied at the shear center, then the beam will bend but does not twist. In symmetrical sections, shear center will coincide with the centroid. So if you take a rectangular and I section, shear center is at the centroid. Okay, so in such cases, shear center will coincide with the centroid. And in a section which has one axis symmetry like the channel section or T section, you can say the shear center will lie on the axis about which the section is having symmetry but will not coincide with the centroid. Okay, this is symmetrical. Suppose if we take this rectangular section, it is symmetrical about xx and yy. So shear center will be there present at the centroid. I section, it is symmetrical about x-axis and y-axis. So shear center is at the centroid. But if you see channel section, C section, it is symmetric about only x-axis, not y-axis. So shear center will not coincide with the centroid. Centroid will be somewhere here. But shear center will be present on the centroidal axis. This is the centroidal axis. Somewhere on centroidal axis, it may be outside also, the shear center is present. Similarly for T section, it is symmetric about y-axis, not x-axis. So the shear center will be present on the somewhere on the centroidal axis, this axis. Okay, that is the meaning of this. Suppose if we see here, the shear center will be on the centroidal axis UU, but not on G. Okay, let us see a problem here. So determine the position of the shear center for a channel section. So there is a channel section given of 120 mm by 120 mm and a 10 mm thickness, 10 mm, 10 mm, 10 mm. So we need to determine the position of shear center. Where is the shear center? Okay, so we know the shear center is somewhere on the centroidal axis. Now if you see, this is a shear flow and this is a centroidal axis, because here centroid will be there, centroidal axis. Shear center, let us assume it is at a distance of E from this point, from some O. Okay, it is exactly center of this one. Okay, so this is E. Now if we find this E, so then that is nothing but we have found the location of the shear center. Okay, now this E we need to find. Let us assume shear force is at a distance of E from the channel web. F be the shear force, F star be the shear force due to shear stress in flange. These are flanges we know, and this is web. Shear force due to shear stress in the flange, and it is at a height of h from the centroidal axis. Okay, h be the height of f dash from centroidal axis. Now let us apply the equilibrium. For equilibrium, clockwise moment about O should be equal to anti-clockwise moment about O. So here, so clockwise moment F star into H. Okay, F star into H is equal to F into perpendicular distance E. So F into equal to F star into H. From here E equal to F star H by F. Let this be equation number 1. To find the position of the shear center of the channel section, we need to find F star. So now we need to find F star. Now what is this F star? Shear force in flange due to shear stress. So shear force equal to shear stress into area. Shear stress is nothing but tau. So F star equal to tau A. Next. So where tau is equal to Fa y bar by Ib. You know this shear stress formula. So F star equal to Fa y bar by Ib into A. Let us find this tau first. Let us find this tau first. Okay. So where F is applied force on the section, A is the area of the flange up to length x. See here we are considering a length x and thickness dx from the tip of the flange as shown in the figure. We are considering small element dx in the flange at a distance of x from this tip, from this tip. Okay, and this is dA, this is D, this is D, right? Sorry, this is dA area and this is A. This is A, area is A. This is dA, this is dA. Right. Now, so A is the area of the flange up to length x. This area. So A equal to 10 into x. Y bar is the distance of center of gravity of area A from neutral axis. Okay, this distance is y bar. Okay, y bar. So y bar equal to 120 by 2, 60 minus 10 by 2. So y bar is equal to 55. Where B is the actual width. I is the moment of inertia of complete section about Ixx. We know this formula Ixx equal to x plus 1 plus Ixx 2 plus Ixx 3. This formula also we know. So Ig1 means BD cube by 12, B1 cube. So let us take it as first section, first, second and third section. 3 sections are there. So if you take the first section, the B value is this one 10 and this is B is 120 and D is 10 and area is 110 into 120. And what is this H1? It is the distance between the central axis and central axis of this particular first section only. Okay, so it is 60 120 by 2 minus 10 by 2. So it is 55. For third section also it is same for this section H3. So 120 by 2 minus 10 by 2. This distance. Okay, same as y bar. It is 55. But if you see this one H2, central axis is this one, and for this second portion also the same central axis. So distance is 0. So 0. Remaining B and D values from figure we can see and we can substitute. So Ixx we will get it as this one. Now substitute in all the values in equation 3, that is in this equation. So F as this, A is 10 into x, 10 into x. Then y bar is 55 we have calculated here. Then I is I value we have calculated here. Substitute, and B is this one, breadth 10. So if you simplify it, you will get it as this one in terms of F into x. Now substitute this. Where we need to substitute this? We need to substitute here. Okay. This is tau value. Now from equation 2, okay, what is equation 2? F star equal to tau into A. Okay, from this equation to F star equal to tau into A. That means you can write integration tau into dA. That is integration tau into what is dA? B into dx. So it is B into dx. B into dx. Okay. Substitute here B into dx. Next. So what are the limits of flange? It is a flange, right? So from here up to this one. So 120 minus 10 by 2. This is 115. So 0 to 115. Substitute tau value. So this is f into x, this is tau, and b is 10 dx as it is. So from here, if we do this integration part, we will get this one. Okay, now substitute in equation 1. Substitute equation. So we'll get e value as 49.28. Okay, after substituting f we get cancelled. So there is an alternative. It is a direct formula for channel section to calculate shear center. Then substitute all the values, you will get 49.28. Okay, h is 110, t1 is 10 thickness, b is 115. Okay, 4 into this already we have calculated. Okay, so b is 115, this distance. Thank you.